Today, I'm going to explain how semiconductors work. Before I do that, though, I need to discuss the concept of band energy. In an atom, an electron can only occupy certain discrete energy levels. Since the energy of an electron increases the farther from the nucleus it is, electrons want to fill the lower energy levels. Now, when you combine a bunch of atoms together, like in a solid, these discrete energy levels combine into a continuous spectrum. This forms the origin of bands. There are two types of bands that are created. The valence band, where the electrons are effectively bound to an individual atom, and the conduction band, where the electrons are free to move throughout the solid. The amount of energy needed to get an electron from the valence band to the conduction band, called the band gap, determines what type of material the solid is. For metals, the conduction band is right on top of the valence band, and no energy is needed for electrons to enter into the conduction band. This means electrons can easily flow throughout the solid, a key characteristic of conductors. In insulators, there is a large energy gap between the valence band and the conduction band. In this case, it takes a lot of energy to get electrons into the conduction band. So, for all common cases, the electrons can't flow, the key feature of an insulator. Semiconductors, then, are in the middle. They still have a band gap, but only a small one. So electrons require only a small amount of energy to jump into the conduction band and begin flowing. Sometimes this energy can be provided by thermal energy in the solid that randomly excites some electrons into the conduction band. So, in other words, semiconductors sort of conduct. In general, thermal energy is a very poor way to increase the conductivity of a semiconductor. Luckily, there are ways to reduce the size of the band gap. This uses the process known as doping. Most semiconductors are made of silicon, which has 4 valence electrons. While these valence electrons can be excited into the conduction band by thermal energy, in general they stay attached to their respective atoms. We can make it easier for electrons to jump into the conduction band by adding more electrons. This is where doping comes in. If we add an element with 5 valence electrons, such as phosphorus, this will add an electron to the silicon lattice. As long as we only add a few phosphorus atoms to the large number of silicon atoms, the phosphorus atoms will take the place of a silicon atom. In this situation, the phosphorus atom only really wants 4 of its electrons, so the 5th can be dislodged with only a small amount of energy. This can be interpreted as decreasing the energy band gap by adding an energy level right below the conduction band. Doping a semiconductor in this way, that adds an electron, creates an N-type semiconductor. You can also dope a semiconductor in the opposite way, by adding a few elements that have 3 valence electrons to a silicon semiconductor. An example of such an element would be germanium. As long as you only add a few germanium elements, they will take the place of silicon atoms, where the germanium wants 4 electrons. However, it only has 3 electrons, so this creates a hole where an electron isn't. For all intents and purposes, this hole can be considered a charge carrier itself. The hole will move when other electrons move to fill the hole's spot, but just ends up creating a new hole. So in this sense, the hole can be seen to travel through the semiconductor in the opposite way of an electron. This also decreases the size of the band gap by adding an energy level right above the valence band for electrons to flow into. This type of doping creates a p-type semiconductor. You can do quite a few interesting things by combining these two types of semiconductors. The first would be making a diode, which only allows current to flow in one direction. You can make this by slapping an N-type semiconductor right next to a P-type. Since N-type semiconductors have a lowered conduction band, and P-types have a raised valence band, an energy gradient is created where the two semiconductor types connect. At this gradient, electrons from the N-type semiconductor fuse with holes from the P-type semiconductor. Note, since the phosphorus in the N-type and germanium in the P-type had the proper number of protons to balance the number of the so-called added or missing electrons, the semiconductors normally have no net charge. However, in a diode, when the N-type electrons move over to join with the P-type holes, both semiconductors become ionized with a slight electric charge. This ionization prevents more N-type electrons from joining with P-type holes. Now, if you apply a voltage, such as from a battery, with the positive end on the N side and the negative end on the P side, N-type electrons and P-type holes will flow away from the gradient. This will actually increase the charge of the semiconductors, making the gradient even steeper and preventing an actual flow of current. However, if you reverse the voltage, so the P side is positive and the N side is negative, then a current will flow. In this case, N-type electrons and P-type holes will flow towards and across the gradient. Once past the gradient, the electrons and holes can easily travel through the rest of the circuit, allowing current to flow. Now, you can make an even more interesting device by either sandwiching a thin P-type semiconductor between two N-types, or a thin N-type between two P-types. This is known as a bipolar junction transistor, abbreviated BJT. And, for the purposes of this example, I will look at the NPN type BJT. Now, since the NPN setup is effectively two dipoles facing in opposite directions, you might think that no current will flow. And if you only have the circuit running from the first N-type semiconductor, which we will call the emitter, through the P-type semiconductor, which we will call the base, to the second N-type semiconductor, which we will call the collector, this would be entirely true. A voltage between the emitter and collector alone cannot cause a current to flow. However, you can get a current to flow through a BJT if you add a circuit between the emitter and base. As long as this second circuit acts in the forward direction, it will draw electrons from the emitter into the base. Since you now have electrons in the base, these electrons can be brought into the collector from the voltage in the first circuit. Most of the electrons will actually flow through to the collector, so the current in the first circuit is a lot higher than the current in the second circuit. The same situation happens with holes if you have a PNP type BJT. You can actually control how much current goes through the emitter to the collector by adjusting the current between the emitter and base. i.e., you can control the magnitude of current in one circuit by controlling the magnitude of current in a separate circuit. So, if we interpret a large current as corresponding to a binary 1, and a small current as corresponding to a binary 0, we have a way to transmit these bits of information. We can then connect multiple circuits to the base, allowing us to determine whether or not the collector current is activated based on whether a couple base currents are activated. This is a logic gate. By more complicated connections of base circuits and combining multiple transistors together, we can create adding machines which can quickly give rise to full-on computers. While this original type of transistor works, it is rather inefficient. To transmit bits of data, you have to constantly apply a current to the base. Luckily, there is an easier way, which relies on a metal oxide field effect transistor, or MOSFET for short. In a MOSFET, you still have either an N or P-type semiconductor sandwiched between two other P or N-type semiconductors, respectively. However, in this case, the central semiconductor, which we will assume to be a P-type for this example, is a lot bigger than the thin base of a BJT. There is then a wire connected to the top of the central semiconductor, which can apply a voltage to the semiconductor. In the case of our example, this wire applies a positive voltage, which draws electrons from elsewhere in the P-type towards the wire. The top part of this P-type semiconductor is now saturated with electrons, making it act like an N-type semiconductor. Since there is no energy gradient between semiconductors of the same type, the truly N-type semiconductors surrounding the P-type that is acting like an N-type can just let current flow. In this way, applying a positive or negative voltage to the middle semiconductor determines whether the transistor acts like a conductor or an insulator, respectively. The reverse situation happens with holes in a PNP type MOSFET. A big advantage to MOSFETs is that minimal energy is needed to maintain the voltage. So this is a much more efficient, as well as faster, way to have a logic gate. However, MOSFETs themselves have limitations. While it doesn't take energy to maintain the voltage on the middle semiconductor, it does take both energy and time to change it. Today's modern computers have pretty much maxed out the switching rate of MOSFET voltages, and require a huge power draw to do it as fast as they do. So, if we want better, faster computers, we're going to need a new type of transistor. The new method of transmitting and manipulating bits will most likely come in the form of adjusting the spin of electrons. However, since these type of computers only exist in a few labs, and discussion of electron spin gets deep into quantum mechanics, I will not discuss this new idea of computing here. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.